and our speaker is Professor Rajiv Kumar, Head Department of Mathematics, Maharishi Dayanand University. So let's all welcome him on the platform. He is also the coordinator of this program. So on behalf of all the organizing team members, sir, I welcome you on this platform. And now over to you, sir.
Thank you, Dr. Ekta and Dr.
Thank you,
Poonam,
sir.
and welcome all the participants who are on the board. I welcome you all on the fourth day of this Gyan course, and of course in the ninth lecture session. You see, all the participants, we are going through the concept of stochastic processes and their applications. And of course, we have taken care of the application in engineering, the application in systems which are used in real life, and we also take care of the real life situations. As you have noticed that Professor Rao, our eminent speaker, who is the foreign faculty, has taken a lot of examples where the stochastic process can be used. Professor Dr. Poonam Redu also taken care of the situation of traffic flow modeling. In my previous lecture, I had discussed about that how stochastic modeling is useful for some engineering or communication systems. How we can have stochastic modeling, and specifically whenever we have the real data, we can collect the real data. Dear participant, you can notice that stochastic modeling can be done for any situation. The thing is, you must be aware about the situation or the system for which you are going to have the modeling. In depth, you should have a knowledge of that system. Only then you can have a fruitful model. You see, models are quite useful for having the depth of the system, its working, its operation, and even for having better predictions. The manufacturers of the system always look for a better system. They wish that their system should work satisfactorily for a longer period of time. And even the system they manufactured, to promote their sale and having more profit, they will look like to have a reliable systems. And even the consumers, users also wish for a reliable system. And that can be ensured by developing stochastic model and looking into the quality, average time of failures, the availability of the system, of course the cost function calculations that has to be taken care by the system provider, as well as this is of interest to the system users or the consumers. So in my previous lecture, I have discussed that how we can have systems modeling. Specifically for communication system, I have taken one example. I have also taken an example for that water process system in a thermal power plant. That was basically a system for which the data we can collect. Now, sometime data is not available. In that situation, you just have the working knowledge of the system, its structure, its component, its repair or maintenance policy. If you have all this information about any system, then you can develop model for that. May not be in the first stance, that model may not be so good, maybe a poor model. But successively you can take care of all the variables or the situations, then you can have a better and better models. So we are always looking for the best model for any situation. Now, that was my concern in the previous lecture, where we have taken this model, taking real data. Today, I'm going to take up another situation where we can have another model which is related to the medical systems, medical science. So I will take two such examples for that. So my lectures is on the topic of analysis of stochastic model for human organ and hospital systems. The outline of my talk will be the first, the introduction, why we look for the stochastic analysis of human organ systems or hospital systems, then how we can develop the models. We should investigate the human organ systems, even if you are not of a background of the medical science. I'm from a mathematics side. My specialization is in operation research and statistics, so I have to go through in depth what is human system, human organ system, what kind of disease can be there, then how the organ fails, what are the reasons behind that, and how the any organ and vital organ deteriorates. Then we have developed the model for the system. So I will take two examples, one related to the hospital dialysis system. You see, this is a biomedical system which assists the doctors and the patients for the dialysis, especially for the kidney case. Another one, I will take another model for the organ itself, the human kidney system. So the introduction part is, my screen is visible to all of you?
Yes, sir, it is
Okay,
visible.
thank you. You see, stochastic model plays a vital role in medical sciences. This is a lot of applications. Here the objective is, you see, I have my initial talk, I have emphasized that before developing the model, you should be clear about the objective of the model. Why you are constructing the model for that particular system or situation. So here I highlighted the main objective of the analysis of stochastic model for medical sciences is to investigate the body organs and disease progressions and to use the analysis in controlling disease related mortalities. Stochastic analysis is quite helpful to us to understand the mechanism of the organs as well as the disease, as it tells us the relationship between the progressions of the disease or the stages of the organs and the all possible covariates. So this modeling is quite useful for all of us. So this is about the organ system, but you see in medical sciences or healthcare industry, the biomedical system is quite important to us because their proper functioning is to be ensured. As for such systems which assist us in medical sciences, whether it is any apparatus or whether it is an instrument to measure the clinical trial, that instruments or that apparatus, that machine should also work satisfactorily, because improper functioning or failure of such machines may cause injury to the patient and even death, and that may of course there can be loss of life, and moreover there can be some legal implication to the doctors or the hospital itself. So therefore the stochastic modeling analysis, especially for the medical science, human organ and hospital systems, taking care of all possible situation and aspect is quite useful, as it is useful to maintain human health and save lives. So my focus today will be on such systems. In previous lecture yesterday, I have given you the steps to develop a stochastic model. The basis is you should have information about the system. Now my system is the human organ system and of course some hospital systems. So we should be clear about the depth, what the system is, how it works, what is the structure of that system, how it gives output, what are the failure possibilities or faults are there in system, and how that fault can be removed, what is the expected life of that system, how we can improve the life of that system, and so on and so forth. So these things has to be taken care, and once the objectives and assumptions are clear, for that particular situation or the model, we can have a mathematical formulation, and then we can successively draw models. Those steps are the same. I'm just showing the slide that we have discussed yesterday. The procedure is same. Here you have to understand the system, its operation, collect relevant data, if it is possible. You see, to collect a data from, you say, any hospital or from a doctor or a patient, as Professor Rao yesterday informed, that is sometimes very difficult to have these data. So that data can be arranged from some resources which are available in the government sources, that may be useful. And even if you can contact some doctors or administrator of the hospitals, they can provide you the data for particular patients or about the particular system they are using, and on the basis of that we can have a modeling. So the rest of the thing is same, the procedure will be same even for that situation. The measure of system effectiveness or performance, whether it is related to organ systems or any medical science system, biomedical systems, almost the common terms are there. You see, first passage time, mean sojourn time, that is useful for us. Reliability of survival illnesses, survivability, life expectancy, availability. That depends that whether it is a living system or a non-living system. Accordingly, we can have these terms, and we may be interested to have these measures. Now, if you are interested to have the modeling and analysis for human organ system, one must be clear about the depth of these aspects. I'm not a student of medical science, but our participants are from some medical side. Some doctors are there on in this GAN course. This is very elementary for them, but I wish to prize all the participants who are from different backgrounds, who are from computer science, or someone is from physics, and someone is from the engineering. That human body system is a entire structure of human being. It has a different, you see, any human body is composed of many different type of cells that together create tissues, and tissues subsequently gives us the organs. Organs, you see, the body is comprises of head, neck, trunk, arms and hands, legs and feet. But we categorize the whole body, human body, into 11 organ systems, and they work together to have a complete body. These systems, you might be aware, are the reproductive system, integumentary systems, muscular system, skeletal system, circulatory system, respiratory system, nervous system, digestive system, excretory system, lymphatic system, and endocrine system. These are the, you see, systems that a human body is composed of. Now, every system involves many organs. For example, if I take integumentary systems, it is having a skin, hair, and nails, and it has a specific function in the body. Similarly, muscular system involves muscles. It has its own functioning. Skeletal system involves bones. It frames, protect, and support the body. Circulatory system is very important and vital system. Heart, blood, and blood vessels, where the blood is pumped and goes through the heart, and body passes through, the blood is passes through the whole body. Respiratory systems involve lungs and nose. Nervous system has brain and spinal cord, which is very, you say, important system. Digestive system, mouth, teeth, stomach, and liver. Excretory, kidney, and urinary system. This is also very important. Then lymphatic system, tonsil and lymph vessels, and so on. You see, I have just given a presenting here slide to apprise you that these systems, I call these as a human organ systems. A system can have one organ or multiple organs. Notice this. Why I'm emphasizing on this? Because yesterday I have taken that whenever you discuss any system, you must be clear about its component. You must be clear about the unit it involves and how those units are arranged. How many components are there in that system? One must be clear. And that's what I want to highlight here. Muscular skeleton system itself is a big system. And you see, you can notice from the second column that it involves different organs and the functioning. One must be clear about the functioning of that system also. Because once you are developing a model and carrying out an analysis, you must be clear that what kind of working of that organ is, the system works, for what purpose it works, and what is the output of that system, how we can improve the quality, that is our target, to improve survivability, that is our target. So one must be clear that the result must be clear to us. Now, you see, when you talk about a system, human body system, if we discuss the failure part of that system, once it fails or deteriorate or degrades, so there can be multiple. Apart from the aging factor, there are some other factors which the body gets deteriorated or organ get deteriorated. So that one thing is the disease. See, one must be clear about the disease, to what disease we are talking about, and what kind of disease a particular organ can have, and what is the fatality of that disease, how that disease prolong, and how that deteriorates the organs. So that should be clear to us before having the modeling. So that's why a disease is any particular abnormal condition which is a disorder of structure or function of the body. In many cases, this is just treated as a disease or disorder or morbidity or illness. Disease can be classified as a communicable disease or non-communicable disease. The disease which travel from one to another body, that is communicable, and some diseases are not non-communicable. I will give you the examples. Further, the disease can be chronic or non-chronic also. So the chronic is which disease that lasts for a longer period of time, usually 6 months or more, and acute disease are the short-lived disease which stand for few days or few hours, and thereafter it subsides. So accordingly, we can have the pattern, the fatality of the disease. If I just classify, there can be four kind of disease categories. Chronic non-communicable disease are the cancer and cardiovascular disease. This is a particular type. Acute and non-communicable, which are acute but not communicable. This is upper respiratory tract infections, myocardial infections, strokes, etc. Chronic communicable disease are the malaria, HIV, hepatitis, TB. Acute communicable disease are cold and flu. So this is a not communicable, but it is not so fatal, now. Of course, the virus these days we are facing, it is a communicable disease, the coronavirus, and that comes into this category. And that's way the people have a lot of modeling on this. Once the organ, apart from, aging factor and having this disease, the whole organ fails. Now in a system, when you say that the organ is failed, because they deteriorate with the stages or with the age, and thereafter all of a sudden it can collapse. Any system, any organ can collapse. That cannot be the vital one, or it depends. Basically, when you talk about the failures, that can be slow, gradual, or it can be instant. So in some organs, this happens instantly. There is a risk of life, but whenever it goes gradually, then the immediate risk of mortality or risk of death is less. So according to American Thoracic Society, organ failure is caused by various factors and conditions, including loss of blood, maybe by any reasons, poisoning, serious trauma, or even drugs, leukemia, or acute illness. So organ failure sometimes involves internal problem or some external interventions also. So organ failure may be chronic or acute. Earlier we have to talk about the disease. The disease can be chronic or acute. Accordingly, the organ failures may be chronic or acute depending upon the kind of disease it has or the aging. Sepsis is the common cause of multiple organ failures. So this is a very serious issue. The vital organ for the body are the liver, kidney, heart, lung, and pancreas. So this may, the failure of these systems can immediately lead to the death of the human body, on any body. So taking these informations, I am just going to take up one example, which is taking a situation of a hospital dialysis system. So I'm considering that system. Once you observe any medical system or the subsystem or biomedical system in a particular hospital, you observe that, and whatever we observed, on the basis of that we have developed a model. So I'm considering here a dialysis system having 6 devices in parallel configuration, and one unit, one device is redundant. So one can say that this is a 6 out of 7 subsystem that we have discussed the different type of redundancies, and that the kind of redundancy I'm taking here. So if I describe the situation and the model, the dialysis system here I'm considering consisting of 6 individual devices in parallel configuration. Parallel configuration, you know what is that parallel configuration, and one redundant device. Parallel configuration as well as one redundant device is there. So total there are 7 devices. 6 are online in parallel and one is spare, because we don't like that dialysis system fails. So redundancy has to be there to have a better dialysis system. When a failure occurs in one of the 6 operative device, then the redundant device is replaced. Say there are 6 devices, उसमें एक उसमें से फेल हो गया, तो जो हमारे पास स्पेयर में पड़ा है जिसको हम कह रहे हैं कोल्ड स्टैंड बाय, उसको हम रिप्लेस कर देंगे और 6 के 6 हमारे डिवाइसेस वर्किंग होंगे और हमारा सिस्टम वर्क करता रहेगा। और मीन टाइम में जब हमने उसको रिप्लेस कर दिया, तो जो डिवाइस फॉल्टी था उसकी हम रिपेयर कर सकते हैं और उसको हम रिपेयर यूनिट के तौर पर, एडिशनल यूनिट के तौर पर हम उसे यूज कर सकते हैं। You know, in a dialysis system, anybody cannot do the dialysis process or maintain the system. There is a specific staff in a hospital. So that is, we assume, we always have a information that in any clinical, a specialized staff is there, or nurses or technician, involving nurses and technician, who can handle the dialysis machine. The observation that we have for a dialysis machine was that it is working 6 hours a day or 6 days in a week, and in that hospital the Sunday was off. The maintenance policy that the dialysis system take cares of is both corrective as well as preventive. Preventive maintenance is required when the system fails, and when it fails, then of course we have to maintain that system. That involve recognition, localization, diagnosis, correction. That is a process. And preventive maintenance is a periodic. Every 16 weeks or 4-month operation, that dialysis machine goes under preventive maintenance. So both kind of maintenance are possible in that things. For having a mathematical modeling of this situation, this system, we have taken some other assumption. System works as new after each repair. The system fails with a constant failure rate, and time of failure are assumed to be exponential. Whereas recovery time we have considered as a general. Switching of the devices, you see, once the device is failed and you replace that device by another one, so that we have assumed is to be a perfect and instantaneous, and all the variables, random variable involved, are mutually independent. We have analyzed this model using semi-Markov process and regenerative point technique. We have taken notations also. Lambda is the constant failure rate of an operative device, and GT, small gt, represent the probability density function of time to repair that device. We need to have some notation for the states. O stands for operative device, CS stands for the cold standby device, that is one device is there. FR stands for failure device, FW stands for the failed device waiting for repair, and F capital R stands for the repair of the failed device which is continuing from the previous stage. This is the state transition diagram for that situation. Here this the first state S0, which is, you see, we are considering O. O means operative units. There are 6 devices within this O, and CS is 1. So initially when the system starts at T0, we assume that the all 6 devices which are operative, they are working well, and one is a spare one, and any one of them devices can fail. The failure rate for one device is lambda, therefore the total failure that can be possible is 6 lambda, and that can goes to S1. So when it go to S1, one device will be failed, and during that time one device which is spare, that will be replaced with the replaced, and the failed device will go under repair. Then at the S1, once the repair of a device is going on and one is already replaced and system is working, there may be possibility that the additional device it may not be repaired and system goes to failure state. So that can again go with the rate lambda, then the system will completely fail. So the dialysis system won't work in that situation. So this is a very simple model where O stand for good state, this stand for square stand for or triangles, rectangle stand for the failed state or down state, and here the dots represent the regenerative points. That once it is repaired, that it will work as good as new. So this is the regenerative point. We have computed the transition probability for this model, and that can be done very in a simple form. Suppose you want to see the transition probability from 0 to 1. So the rate is 6 lambda, and it is a constant. So this will be follow exponential distribution. So the probability for transiting from 0 to 1 can be written as a dq 0 to 1 6 lambda e power minus 6 lambda dt. This is a differential.
Sir,
Yes,
sorry
please.
to interrupt. Sir,
Yeah.
I want to make one thing clear. There are six devices.
Yeah.
All are different, sir.
All are same.
All are same. Thank
All
you.
are same.
Right.
We have taken the situation which all 6 devices which are working operating they are same, and the
Yes.
additional device which is a spare that is also one same one.
Yeah, right. Sir.
Okay.
Thank you, sir.
So that's why I'm calling it as a 6 out of 7. 6 out of 7 all are identical. Each of them has a failure rate lambda, and that's why we can have 6 lambda e minus 6 lambda t. However, we can generalize this model. You see, this was a situation that we have observed. But suppose you have a system where all the units are not identical, then we can also find out the transition probabilities. But there in that situation, we have to write the lambda 1 plus lambda 2 plus lambda 3. So lambda 1 is assumed to be the failure rate of the first device. Lambda 2 is the failure rate of the second device. So that will be lambda 1 plus lambda 2 and so on up to lambda 6. That way you can do. So similarly, if I look for the probability from 1 to 0, so this will be only possible when where it is a repaired. So the repair rate is there e power minus 6 lambda t because it is not going to the next state and it will be g1 t. So this is a combined total probability that if you are going from state 1 to 0 state, you take care that you should not move to S2 state. So if you want to see that what are the chances that the system goes to S0, so you had to preclude the situation that S1 will go to S2. So S1 will go to S2, that probability we know that will be 6 lambda e power minus 6 lambda. But if it is not going to that way, that will be e power minus 6 lambda t, complement law of the exponential distribution, non-occurrence of the event. So that will be e minus 6 lambda t and occurrence of the event g1 t dt. This is a, you see, I'm using multiplicative law of probability. Similarly, if you are going from 1 to 2, that way we can compute these probabilities. And whenever, this is an example where we have non-regenerative state. Here, this is a non-regenerative state. Dot represent the regenerative states, and this represents going from S1 to S2 is a non-regenerative state. So therefore, in that situation, you can have a different symbol. You can notice it that for the case of S1, where we have taken failure as f small r, but in case of S2, we have taken the failure of additional unit as capital F with the suffix capital R. So capital R stands for that the repair is continuing from the previous stage. So this lead us to a non-regenerative state. In non-regenerative state, the system won't stop here. It is continuing from the previous case, and therefore, in that situation, if you are looking for the probability from transiting of the system from 1 to 2 or 2 to 1, in that situation, we have to take care of the non-regenerative points. And that's why shifting from 1 to 2, 6 lambda e minus 6 lambda t g1 bar t, that is the complement of g1 t PDF, this will be the CDF, and from going 1 to, the system won't stop at 2. So therefore, we are moving from 1 to 1 via 2. That is called 1 to 1 via 2. And in that situation, the probability function will come out to 6 lambda e minus 6 lambda t convolution G1T. Now, this is a, you see, the probability, and we are looking for the steady state probability. These are the transient probabilities. These are difficult to solve. So if you take a steady state probability, in that case, Pij limit s goes to 0, that we can take. And of course, this in that case, this will be t goes to infinity. If t goes to infinity in Laplace transforms for a function, we can take limit s goes to 0. That I have shown in the last lecture, in my last lecture. In that situation, the steady state probability will come out to be like this. You can check that in any state, the total probability of transiting to any other state should be 1, and that we have noticed. We can compute the mean sojourn time at the state 0, mean sojourn time at the state 1. These are the computed values. The mean sojourn time at the stage 2 is not evaluated because that was a non-regenerative state, and unconditional mean times are also computed for the stages. Mean time to system failures, that formula we know, and in this case it come out to be x over y, where x stand for the value, numerator value, mu0 plus mu1, and y is p12. This is the probability. Availability of the system, that at a particular time, what is the probability the system is available? That dialysis system is available for the patient. So that is also computed for this. So that is A3. You see, in medical sciences, for such systems, stochastic modeling is not much has been taken up, and the people are working on this direction. This is of course a new area. So you can have very simple, you take a simple situations, and you can take organs and their position, their states, and accordingly you can carry out the analysis on the basis of the information provided by the doctors or the patient, or even from the some official records. You can have different states and different reasons for achieving those states and remedies or diagnose or recoveries. On the basis of that, we can see for any systems. So this is the availability we have computed. I just want to show you that how we work for this. Expected time to repair the system. Now, if there is a failure of a device, the maintenance team is there to repair that. Technicians are there to maintain the device, or even when the whole system goes to the failures. So what is the time to repair the system if there is some sort of failure? So the busy period for maintenance staff is computed using the same logics, drawing the recursive relations and solving recursive relations. We have B3, X2 or Y1, where X2 is you see this function. I'm skipping mathematical part just to show that how we compute the measure and how we do the analysis. If someone is interested, you see the paper is already published that can be available, and I also already mentioned to you to the books. The mathematics is given in all those books. We may be interested in expected number of visits of the maintenance staff. So these measures can vary from system to system. Notice it. The measure of effectiveness of the system or the measure of performance that of the system can vary depending upon the situations, and accordingly we have to find out these measures. So what is the average or mean value, average number of visits of maintenance staff that we can compute? What is the profit if suppose a hospital purchase a device for dialysis, that is a dialysis system, how much they gain from the dialysis system from the patient, and what cost they have to bear, and what maintenance charges or you say they have to bear with that system over the years or for the period that system was. Then we can also see profit or the cost analysis can be done. If we take a very simple logic, a simple formula that all these are then linear related, costs are linear related, where 0 stand for revenue per unit uptime of the system that the dialysis system is working, and what is the revenue per unit time, and C1 stand for cost per unit time for which the maintenance team is busy for the repairing for that particular system. C2 stand for cost per visit of the maintenance team while visiting. The team may be there in the hospital itself, or team, you see some for sophisticated systems, dialysis systems, team has to be invited from the system provider. They take charges if the maintenance is not free. Then C2 is the cost per visit of the maintenance team, and C3 stand for the cost per unit installation of the system. And this calculation is per unit installation, And if we compute this, profit analysis can also be carried out. Since we have taken here repair rate as a GT, for a simplicity, we have assumed that G1T is a exponential rate. That is, it is a repair is being done with the constant repair rate beta, and therefore beta E minus beta T. And for this, we have computed the calculation, carry out the computations for the steady state probability, and all the measures are computed for this particular case. Then we can have a graphic analysis. You can plot a failure rate of a particular device lambda versus the mean time to system failure. This is the same thing that we have discussed yesterday in my lecture, that we lambda MTS, mean times to system failure, represent the reliability of the system. So as the lambda goes, you can see that the MTSF goes down, and beta stands for the repair rate. And if repair rate goes higher and higher, then obviously the mean time to system failure or the reliability of the system improves. Similarly, if we plot for other betas, we can have these values. We can show the availability of the system also. Availability of the system is also plotted with respect to lambda. Same pattern have been observed for the availability also. We check out that how long the system is profitable for the hospital. So failure rate versus profit is plotted. You can notice that this curves cuts at x-axis at some betas. So beta is to be taken as a 0.5, 1.5, 2.5. That is in 1 hour, 0.5 repairs are done, and so on and so forth. So this cutoff points may be of our interest, that how long the system is profitable. So this cutoff point will show us the positive profit. Upper side of above the x-axis, this will be showing positive profit, and below the x-axis, it is showing the negative profit. So in that case, if it is a positive profit, that is of our interest. So we can locate those points at what failure rate, at what recovery point that the system is profitable for the hospitals. Similarly, we can have a cutoff point for the revenue, how much revenue to be generated for having the system to be profitable for the hospital, for the doctors. So revenue versus profit is plotted. So you can see that if revenue is say rupees 403 rupees and 45 paisa, in that situation for C1 is equal to 40, the system is profitable. And what is you see, C1 was you can notice that C1 was the cost per unit time for which the maintenance team is busy. So when the maintenance team is working there and their cost is assumed to be 40 rupees, in that situation, cutoff point indicates that the system will be profitable whenever the revenue generated per unit is more than 403 rupees 45 paisa. Similarly, if maintenance cost per busy period of the maintenance is 120, then it should be 499 rupees 60 paisa. Cutoff point. This shows the profitability. Otherwise, there will be a loss from the system. And if C1 is 200, and the cost of maintenance is come out to be rupees 200 per unit, in that situation, the revenue must be fixed as 595 rupees 465 paisa. So that indicates that what revenue should be there from the unit. So only then it will be profitable. Otherwise, it's not profitable. So you see, if we are talking about the profitable, we are also talking about the quality of the machine, efficacy of the machine. So that is it. We can compute in terms of MTSF, reliability of the system. And if you take in terms of the cost, we can see the cost from these cutoff points, that what should be the cost or revenue generated from a system. So that will give you the trade-off between the reliability and the cost. So in any system, what you say interest is of having the trade-off between the reliability or availability, that is the performance of the system, and the cost of the system. So these two can be analyzed with respect to this. I take another example. And now I'm not taking medical system, rather I am taking care of the organs. And if we consider a human kidney system, where we assume that there is some kind of CKD, chronic kidney disease. So let me apprise you that kidney is a very vital organ in the body. As you know, this is a vital organ that maintains the health, because it is, you see, composition of blood in the body is balanced through the kidney, and cleaning of the blood is also through that. Basically, in any kidney, there can be two kind of disease which are very common. One is categorized as acute kidney injury (AKI). Other one is a chronic kidney disease (CKD). Acute kidney failure leads to completely fail of the kidneys immediately, suddenly. So that is a very risky one. CKD is a situation where the kidney functioning goes slightly decline slowly and slowly. So this is gradually the kidney goes down. So that is the situation. And how much kidney functions, that will be that is computed through glomerular filtration rate, which is a medical term, technical terms. The doctors who are here, they can understand what is GFR. I'm not going to the depth of the GFR. Anyways, GFR is a measure which shows that how much kidney is working. Chronic kidney disease usually developed in the stages. You see, if we talking about CKD, so that is happens in slow manners, and we can have different stages for the kidney in that situation. So if the kidney CKD is detected at the early stage, so that can be managed. But if CKD is detected at the say later stage, in that situation it is very difficult to have to save the patient. So that is a very important point because we have to take care of the CKD and different stages of the system. I just want to show you that this is the situation which a doctor in journals, these figures are available. Even if you go for any health report related to kidney, you will see that these are the stages. Stage 1 of the kidney is taken whenever GFR is greater than 90, that the kidney damage with normal GFR. It is not serious case. The other stages of the kidneys is when GFR is lying between 60 to 89. Then there is a mild reduction in GFR. If it is 30 to 59, there is a moderate reduction in GFR. And if it GFR comes out to be between 15 to 29, these are, you see, different American reports and health report. There are, as Professor Rao was informing us about the WHO reports and other reports, American Health Organization report. They can have little variations. But if you go for a reliable resources that we have taken from American reports, and on the basis of that, we are having these figures. So these 5 stages are there, and whenever GFR is less than 15, then kidney fails. The only possibility is then is to kidney you have to replace, the doctor has to replace the kidney. Now this is the 5 stages you can notice. Now these taking care of these 5 stages and taking care that there is a CKD, not we are not taking care of AKI. Then other assumptions which are required to modeling, mathematical modeling of this is we had taken observation. Of course, the assumption, whatever assumption you take for any model, that should seem to be fitted to the situation. They seem to be reliable. Of course, we like that the lesser number of assumptions should be there for the model. But sometime you see, if we are not having much information about the system, then we may have more assumptions. You see, the model is itself a set of assumptions. The single treatment diagnosis facilities available. Generally, this happens. Okay, there is not a multiple facilities in hospitals. Single treatment diagnosis facilities are available. In a bigger hospital, of course, there are multiple machines. The patient reaches the hospital in negligible time, and treatments for recovery and transplantation of the organ in the hospital starts with the all medical perfection and accuracy. We assume that the all other things are taken care. Times to damage or failure or initial recovery in the hospital treatment of the organ have exponential distribution, whereas the other distribution are assumed to be general. Random variables, all whatever the random variable T time and other things are to be taken to be mutually independent. Transplantation of the kidney is perfect and instantaneous. We have taken a care of the situation when totally kidney fails and we transplant the kidney. We have taken that situation here. The transplanted kidney works as good as new. Yeah, I think the hand is raised by Dr. Manju, I can see.
Yes, sir.
What is the
Yes, sir.
doubt?
Sir, what about the assumption third and fourth? Are these really fulfilled, or just we are assuming? How we can confirm these assumptions?
Yeah, that assumption, you see, we have taken this assumption here, and that's why I'm calling it as assumption. Basically, this cannot be verified from the system that we have taken there, because damage of this machine the failure that are occurring here, initial recovery and hospital treatment of the organ. All these things, the data as such was not available from that dialysis machine, for that dialysis machine. And we have taken the stages of the system from the a medical report, and observing the systems, we have taken these constant rate of failures, constant rate of damage, and constant rate of recovery for that particular system. If a real data is available from here, you see, I have not mentioned that it is a real data is available to us. If real data is available, then of course we can verify whether this rate is constant or not. Is this exponential or not? You see, exponential distribution for the failure rate is very common, and because of many reasons. One thing is it is representing the constant failure rate. Secondly, this is quite easy to handle exponential distribution. Thirdly, whenever you carry out the analysis, exponential distribution has a one property that you might be aware. It has a Markov property, and we are doing Markov analysis. We are using semi-Markov technique. So Markov technique required that the past does not depend upon the future, but it may represent present, depend on the present. That is the past. Future is not affected by the past, but it may be affected by the present. So that is Markovian property has to be there if you are going to have Markov process, assuming it is a Markov process, and you are want to carry out the analysis using that concept. So exponential distribution satisfies that property also, and therefore this seems to be very logical and genuine that we can assume the exponential distribution. If you have a data, of course, we can fit the exponential distribution, we can verify it.
Thank you, sir.
Okay. These are after taking these assumptions and some notations.
Excuse me, sir.
Yes, please.
Sir, timing for the first lecture is already over, sir. Can you wind up in within 5 minutes?
Yeah, sure. Thank you, Dr. The notations we have taken as a damage rate from kidney, normal kidney to kidney stage 1. We have taken it as lambda 02, kidney stage 1 to kidney stage 2, lambda 12. Taking these notations, and of course, G1T represent the time to medically treat the patient at kidney, patient having kidney at stage 1. G2 represent the patient having kidney stage 2. ST is the rate of transplantation of the kidney if it is required. This is an artificial kidney that is replaced by some other kidney, or artificial, we can call it as an artificial kidney. In that situation, we have this state transition diagram. You see, they can have different stages depending upon different states depending upon the stage of the kidney, and that's why we have different here blocks here. O stand for normal state, hexagon stand for minor degraded state, that is the first stage of the kidney. This pentagon major failure state, that is the second stage, and triangles represent the degraded state with one failed unit, that is one kidney is failed, and this represents the complete failure of the kidney system, excretion system. So transition probability for this is also computed in the same fashion as we have discussed in the previous model, as mean sojourn times, unconditional mean times, mean time to system failure, expected time to the hospital treatment for that kidney patient. What time is there, average time in the hospital for the kidney patients, and computation of this, and how many time that on average that he has to visit the hospital for dialysis or for treatment of the kidney, or even for transplantation. So that number is also computed, and this is the pattern of mean time to system failure. And for the kidney system, we call it as a instead of MTSF, we call it as a survivability. So survivability versus damage rate is shown by this figure. One can also call it as a mean survival rate. So mean survival time and damage rate, that is plotted, and we have observation. This was the interpretation that we can have graphical interpretation from each of the graph, and this is about all my talk for today. I have taken an example of no doubt a dialysis system and a kidney system, but if you are interested for the other system, some of my students are working on, of course, the liver system and liver organ and heart organs, and some are working on different kind of disease like cancer and so on and so forth. A team of 3 4 students are working with me in coordination with the Professor Rao and some doctors. So you can also, if are interested for having research in this area, this is a very that is potential in this area, and moreover this is a quite useful also. And I want to apprise the participants in this direction. The projects are easily available by different funding agencies. Of course, this is a very better area of research for the promotion of healthcare as well as the survivability of the human being. So during this corona period also, pandemic situation, lot of such models have been developed and analyzed for the future predictions. So thank you very much for patient listening. And if you have any question, I will be happy to answer such questions. Yes, anyone? Any question from your side? Okay, if it is not, so thank you very much to the coordinating team, Dr. Ekta and Poonam, giving me this chance to I have some sharing knowledge from my side to the participant. And thanks to all the participants who have joined over here. Thank you very much for patient listening. And of course, we will proceed for the further lectures. Thank you very much. Thanks all.
Thank you so much, sir, for your informative lecture, and thanks all the participants for patient listening. Now, before starting our next session, one important announcement for all the participants that tomorrow, between 5 to 6 p.m., we have a quiz for you. That will be organized by Google quiz form, and it will be of 25 marks. Yes. It will be of 25 marks. So we will, and in next session also we will share attendance form. So kindly fill your attendance form as we can